Welcome to Chemistry, classifying redox reactions. Oxidation and reduction are the two halves of one of the most important classes of chemical reactions on Earth. Every time iron rusts, every time a battery delivers current, every time a plant converts carbon dioxide and water into sugar, every time your body breaks down food for energy, a redox reaction is at work. In this presentation, we will build a complete picture of what redox really means. We will start with the language of oxidation and reduction, learn how to assign oxidation numbers, and master the four main categories of redox reactions: combination, decomposition, single displacement, and combustion. We will also meet a fascinating special case called disproportionation, where one element is both oxidized and reduced at the same time. We will finish with a powerful method for balancing any redox equation, explore the real-world applications that make redox the backbone of energy, biology, and industry, and test your understanding with 5 multiple-choice questions and 5 fully worked problems. By the end, you will be able to recognize, classify, and balance redox reactions with confidence. The word redox is a contraction of reduction and oxidation. A redox reaction is any chemical reaction in which electrons are transferred from one species to another. Oxidation and reduction always happen together, never alone. Oxidation is the loss of electrons. When a species loses electrons, its oxidation number increases. We remember this with the mnemonic OIL reg. Oxidation is loss. Reduction is gain. Reduction is the gain of electrons. When a species gains electrons, its oxidation number decreases. The species that loses electrons and is oxidized is called the reducing agent because it is the substance that gives electrons to the other species and thereby causes the other species to be reduced. The species that gains electrons and is reduced is called the oxidizing agent because it is the substance that takes electrons and thereby causes the other species to be oxidized. So the reducing agent gets oxidized and the oxidizing agent gets reduced. This swap is the heartbeat of every redox reaction in the universe. At the heart of every redox reaction is the transfer of one or more electrons from the reducing agent to the oxidizing agent. Consider the classic reaction between sodium metal and chlorine gas. Solid sodium metal reacts with chlorine gas to form sodium chloride, ordinary table salt. The sodium atom starts with oxidation number 0 because it is in its elemental form. It ends with oxidation number +1 because it has lost one electron to become the sodium ion in the salt. So sodium is oxidized. Meanwhile, the chlorine atom starts with oxidation number 0 in the diatomic Cl2 molecule. It ends with oxidation number -1 in the chloride ion because it has gained one electron. So chlorine is reduced. In the process, one electron has moved from sodium to chlorine. We can write this as two half reactions. Oxidation half reaction. Na gives Na plus E minus. Reduction. Half reaction. Cl2 plus 2E minus gives 2Cl minus. When we combine them, the electrons cancel, and we get the full balanced equation 2Na plus Cl2 gives 2NaCl. This pattern of writing oxidation and reduction as two separate halves is the foundation of the half reaction method for balancing redox equations. Oxidation numbers are the bookkeeping tool that lets us keep track of where the electrons go in a redox reaction. The oxidation number of an atom in a pure element is always 0. This applies to monatomic elements like copper, to diatomic molecules like O2 and Cl2, and to more complex allotropes like white phosphorus, P4. In a monatomic ion, the oxidation number equals the charge of the ion. Sodium in Na plus is +1, oxygen in O2 minus is -2, and iron in Fe3 plus is +3. For neutral molecules, the sum of all the oxidation numbers must equal 0. For polyatomic ions, the sum of all the oxidation numbers must equal the charge of the ion. Fluorine is the most electronegative element, and it is always assigned -1 in compounds. Oxygen is almost always -2, except in peroxides like hydrogen peroxide, where it is -1. Hydrogen is +1 when bonded to nonmetals and -1 when bonded to metals, as in metal hydrides. Group 1 metals are always +1. Group 2 metals are always +2. With these simple rules, we can assign oxidation numbers to almost any atom in almost any compound, and therefore identify which atoms are being oxidized and which are being reduced. A combination reaction, sometimes called a synthesis reaction, is a redox reaction in which two or more substances combine to form a single product. The general pattern is A plus B gives AB. Many combination reactions involve a metal reacting with a nonmetal. For example, two sodium atoms combine with one chlorine molecule to form 2 units of sodium chloride. Two aluminum atoms combine with 3 bromine molecules to form 2 units of aluminum bromide. The metal is oxidized because its oxidation number goes from 0 in the element to a positive value in the compound. The nonmetal is reduced because its oxidation number goes from 0 to a negative value. Combination reactions can also involve two nonmetals. For example, sulfur burns in oxygen to form sulfur dioxide. Carbon burns in oxygen to form carbon dioxide. Nitrogen reacts with hydrogen under high pressure and temperature to form ammonia in the famous Haber process. In every case, two reactants become one product, and the oxidation numbers of at least two elements change. Combination reactions are the workhorse of inorganic synthesis, and many of the most useful compounds in chemistry are made by this route. A decomposition reaction is the reverse of a combination reaction. A single compound breaks down into two or more simpler substances, and the general pattern is AB gives A plus B. The most common decompositions are caused by heating, and they often involve the breakdown of an unstable compound into its elements or into a more stable compound plus an element. For example, the electrolysis of water breaks it down into hydrogen and oxygen. The thermal decomposition of mercury 2 oxide gives liquid mercury and oxygen gas. This was the reaction that the chemist Joseph Priestley used to discover oxygen in 1774. The decomposition of hydrogen peroxide gives water and oxygen gas, a reaction used in rocket propulsion. The decomposition of potassium chlorate in the presence of a manganese dioxide catalyst gives potassium chloride and oxygen, the laboratory source of oxygen gas. In every decomposition reaction, at least one element changes its oxidation number. The element that started in a positive oxidation state in the compound is reduced to 0 in the element, and any element that started negative, like oxygen in an oxide, is oxidized to 0 in the element. Decomposition reactions are the workhorse of analytical chemistry and metallurgy. A single displacement reaction, sometimes called a single replacement reaction, is a redox reaction in which one element replaces another element in a compound. The general pattern is A plus BC gives AC plus B. A more reactive element kicks out a less reactive element from its compound. Whether a displacement actually happens is predicted by the activity series, a ranked list of metals from most reactive to least reactive. Any metal higher in the series will displace any metal below it from a solution of its salt. For example, zinc is more reactive than copper, so a strip of zinc placed in a solution of copper 2 sulfate will dissolve, and copper metal will plate out on the strip. The zinc is oxidized, going from 0 to +2, and the copper is reduced, going from +2 to 0. Hydrogen can also be displaced from acids by metals that are more reactive than hydrogen, like magnesium, zinc, and iron, but not by copper, silver, or gold. We can also have displacement of halogens. Any halogen higher in the activity series will displace a halogen below it from its salt solution. Fluorine is the most reactive halogen, followed by chlorine, bromine, and iodine. A combustion reaction is a redox reaction in which a substance reacts rapidly with oxygen, usually a gas, to release heat and light. The most familiar combustion reactions are the burning of hydrocarbons and other fuels. When methane, the main component of natural gas, burns in oxygen, the products are carbon dioxide and water vapor. The carbon in methane has oxidation number -4, and in carbon dioxide it is +4, so carbon is oxidized. The oxygen in O2 is 0, and in carbon dioxide and water it is -2, so oxygen is reduced. The combustion of propane, C3H8, gives carbon dioxide and water. The combustion of octane, C8H18, the main component of gasoline, gives carbon dioxide and water. Combustion does not have to be limited to hydrocarbons. Metals can combust too. Magnesium burns in oxygen with a brilliant white flame to form magnesium oxide. Iron burns in pure oxygen to give iron 3 oxide. Hydrogen burns in oxygen to give water. In every combustion, oxygen is the oxidizing agent, and the substance that burns is the reducing agent, even though we do not usually call it that for everyday burning. A disproportionation reaction is a special and beautiful kind of redox reaction in which the same element is both oxidized and reduced. The element starts in an intermediate oxidation state, and some of the atoms go up in oxidation state while other atoms of the same element go down. The classic example is hydrogen peroxide. In hydrogen peroxide, H2O2, oxygen has oxidation number -1. In the presence of a catalyst like manganese dioxide, hydrogen peroxide decomposes into water and oxygen gas. In water, oxygen is -2, having been reduced. In oxygen gas, oxygen is 0, having been oxidized. So the same element, oxygen, is both oxidized and reduced in the same reaction. Another famous disproportionation is the decomposition of potassium chlorate, KClO3, into potassium chloride and oxygen. The chlorine starts at +5 and goes to -1 in KCl, while the oxygen goes from -2 to 0 in O2. Wait, in that case, it is actually the oxygen that disproportionates, not the chlorine. The reaction of chlorine with cold, dilute sodium hydroxide gives sodium chloride and sodium hypochlorite, which is the active ingredient in household bleach. Here, chlorine starts at 0 and goes to both -1 and +1. This is a true disproportionation of chlorine. Some redox equations can be balanced by simple inspection, but many cannot. For those, the half reaction method gives a reliable, systematic procedure. We split the overall reaction into 2 half reactions, an oxidation half and a reduction half. For each half reaction, we first balance all atoms except hydrogen and oxygen. Next, we balance oxygen by adding water molecules, usually to the side that is short on oxygen. Then we balance hydrogen by adding H+ ions if the reaction is in acidic solution, or OH- if it is in basic solution. For acidic solution, we balance the charge by adding electrons to the more positive side. For basic solution, we add OH- equal to the number of H+ to both sides, which converts H+ to water. Then we balance charge with electrons. Once both half reactions are balanced, we multiply each by a factor so that the number of electrons lost in the oxidation half equals the number gained in the reduction half. Then we add the 2 half reactions together. The electrons cancel. We cancel any water molecules that appear on both sides. What remains is a balanced overall equation. This method works for every redox reaction, no matter how complex. Redox reactions are everywhere, and modern life depends on them. In batteries and fuel cells, a spontaneous redox reaction is split into 2 half reactions at 2 electrodes, and the electrons are forced to travel through an external circuit, producing an electric current. The lead-acid battery in every car, the lithium-ion battery in every phone, the hydrogen fuel cell powering the next generation of vehicles, all work on this principle. In corrosion, the reverse happens. Iron rusts when it is oxidized by oxygen in the presence of water. The economic cost of corrosion runs into the hundreds of billions of dollars every year. In biology, cellular respiration is a controlled redox reaction in which glucose is oxidized to carbon dioxide and oxygen is reduced to water, releasing the energy that powers every muscle, every thought, every heartbeat. Photosynthesis is the reverse. Plants use the energy of sunlight to reduce carbon dioxide to glucose and oxidize water to oxygen, filling the atmosphere with the oxygen we breathe. In industry, redox reactions extract metals from their ores, bleach paper and textiles, purify drinking water, and produce the fuels that keep the world running. Let us pull together the main ideas before we test them. A redox reaction is any reaction in which electrons are transferred from one species to another. Oxidation is the loss of electrons, and reduction is the gain of electrons. The substance that loses electrons, the reducing agent, is itself oxidized. The substance that gains electrons, the oxidizing agent, is itself reduced. We track electron movement with oxidation numbers, assigned by a fixed set of rules. Pure elements are 0, monatomic ions equal their charge, oxygen is almost always -2, hydrogen is +1 with nonmetals. There are 5 main classes of redox reaction. Combination reactions, where 2 or more substances form one product, A plus B gives AB. Decomposition reactions, the reverse, where one substance breaks into 2 or more, AB gives A plus B. Single displacement reactions, where one element replaces another, A plus BC gives AC plus B. Combustion reactions, the rapid reaction with oxygen. And disproportionation, where the same element is both oxidized and reduced. The half-reaction method provides a systematic way to balance any redox equation in acidic or basic solution. These are the tools you will need for the quiz and problems ahead. Question 1. In the reaction 2Fe plus 3Cl2 gives 2FeCl3, which element is the reducing agent? Option A, Fe. Option B, Cl. Option C, FeCl3. Option D, Cl2. Take a moment to work it out. The correct answer will appear in 60 seconds. Question 2. What is the oxidation number of sulfur in the sulfate ion? SO4 with a charge of -2? Option A, +6. Option B, +4. Option C, -2. Option D, +2. Take a moment to work it out. The correct answer will appear in 60 seconds. Question 3. Which type of redox reaction is described by A plus B gives AB? Option A, decomposition. Option B, single displacement. Option C, combination. Option D, combustion. Take a moment to work it out. The correct answer will appear in 60 seconds. Question 4. In the decomposition of hydrogen peroxide, 2H2O2 gives 2H2O plus O2. What happens to the oxygen? Option A, it is only oxidized. Option B, it is only reduced. Option C, it is both oxidized and reduced, a disproportionation. Option D, its oxidation number does not change. Take a moment to work it out. The correct answer will appear in 60 seconds. Question 5. A strip of copper metal is placed in a solution of silver nitrate, AgNO3. Will a reaction occur? Option A. Yes, copper will displace silver. Option B. No, copper is less reactive than silver. Option C. Yes, silver will displace copper. Option D. No, because silver nitrate is not soluble. Take a moment to work it out. The correct answer will appear in 60 seconds. Problem 1. Determine the oxidation number of manganese in potassium permanganate, KMnO4. The formula unit has a charge of 0. We apply the rules. Potassium is a group 1 metal, so its oxidation number is +1. Oxygen is almost always -2, and there are 4 oxygens, so the total from oxygen is 4 times -2, which equals -8. Potassium contributes +1, oxygen contributes -8. The sum must equal 0, the charge of the formula unit. So +1 plus the oxidation number of manganese plus -8 equals 0. The oxidation number of manganese equals 0 minus +1 plus 8, which equals +7. Manganese is +7 in K equals 0, 4. This high oxidation state is what makes permanganate such a powerful oxidizing agent in acidic solution. Problem 2. Aluminum metal reacts with oxygen gas to form aluminum oxide. Write the balanced chemical equation and identify which element is oxidized and which is reduced. Step 1. Write the unbalanced equation from the description. Aluminum Al plus oxygen, O2, gives aluminum oxide, Al2O3. Step 2. Balance the equation. We need 2 Al on the left to balance the 2 Al on the right. We need 3O on the right, which means we need 3 halves of O2 on the left. Multiplying through by 2 gives 4Al plus 3O2 gives 2Al2O3. Step 3. Assign oxidation numbers. Aluminum goes from 0 in the element to +3 in the oxide, so aluminum is oxidized. Oxygen goes from 0 in O2 to -2 in the oxide, so oxygen is reduced. Aluminum is the reducing agent, and oxygen is the oxidizing agent. Problem 3. A strip of zinc metal is placed in a solution of copper 2-sulfate. Predict what happens and write the balanced net ionic equation. Step 1. Consult the activity series. Zinc is more reactive than copper, so zinc will displace copper from solution. The reaction is spontaneous. Step 2. Write the molecular equation. Zn solid plus QSO4 aqueous gives ZnSO4 aqueous plus Cu solid. Step 3. Write the complete ionic equation. Zn solid plus Cu2 plus aqueous plus SO42 minus aqueous gives ZnN2 plus aqueous plus SO42 minus aqueous plus Cu solid. Step 4. Cancel spectator ions. Sulfate appears unchanged on both sides, so it cancels. The net ionic equation is Zn solid plus Cu2 plus aqueous gives Zn2 plus aqueous plus Cu solid. Step 5. Identify the redox. Zinc goes from 0 to +2, so it is oxidized. Copper goes from +2 to 0, so it is reduced. Zinc is the reducing agent, and the copper 2 ion is the oxidizing agent. Problem 4. Balance the following redox equation in acidic solution. Cr2O72 minus plus Fe2 plus gives Cr3 plus plus Fe3 plus. Step 1. Split into half reactions. Oxidation. Fe2 plus gives Fe3 plus. Reduction. Cr2O72 minus gives Cr3 plus. Step 2. Balance the reduction half. There are 2 Cr on the left, so we need 2 Cr3 plus on the right. The 7 oxygens on the left are balanced by adding 7 H2O on the right. The 14 hydrogens are balanced by adding 14 H plus on the left. The charge on the left is -2 plus 14 times +1, which equals +12. The charge on the right is 2 times +3, which equals +6. To balance, we add 6 electrons to the left. Reduction. Half. Cr2O72 minus plus 14H plus 6E minus gives 2 Cr3 plus 7H2O. Step 3. Balance the oxidation half. The charge on the left is +2. The charge on the right is +3. Add 1 electron to the right. Oxidation, half, Fe2 plus gives Fe3 plus E minus. Step 4. Equalize electrons. Multiply the oxidation half by 6. 6 Fe2 plus gives 6 Fe3 plus 6 E minus. Step 5. Add the half reactions. Cr2O72 minus plus 14H plus 6 Fe2 plus gives 2 Cr3 plus 7H2O plus 6 Fe3 plus. Problem 5. The combustion of propane, C3H8, is the reaction that fuels gas grills and home heating. The unbalanced equation is C3H8 plus O2 gives CO2 plus H2O. Step 1. Balance carbon. There are 3 C on the left, so we need 3 CO2 on the right. Step 2. Balance hydrogen. There are 8 H on the left, so we need 4 H2O on the right. Step 3. Count oxygen on the right. 3 CO2 contributes 6 O, and 4 H2O contributes 4 O, for a total of 10 O. Step 4. Balance oxygen. 10 O means we need 5 O2 on the left. The balanced equation is C3H8 plus 5O2 gives 3 CO2 plus 4 H2O. Step 5. Identify the redox. Carbon goes from an average oxidation state of -8/3 in propane to +4 in CO2, so carbon is oxidized. Oxygen goes from 0 in O2 to -2 in CO2 and H2O, so oxygen is reduced. Propane is the reducing agent, and O2 is the oxidizing agent. Step 6. A stoichiometric bonus. The complete combustion of 1 mole of propane consumes 5 moles of O2 and produces 3 moles of CO2, useful for any gas law calculation on the products of combustion. Let us bring everything together in a comprehensive review. A redox reaction is any reaction in which electrons are transferred from one species to another. Oxidation is loss of electrons, reduction is gain of electrons, and the two always occur together. The reducing agent is the species that loses electrons and is itself oxidized. The oxidizing agent is the species that gains electrons and is itself reduced. We track electron flow with oxidation numbers, assigned by fixed rules. Pure elements are 0, monatomic ions equal their charge, oxygen is almost always -2, hydrogen is +1 with nonmetals, fluorine is always -1. There are 5 main classes of redox reaction. Combination, where A plus B gives AB. Decomposition, where AB gives A plus B. Single displacement, where A plus BC gives AC plus B, governed by the activity series. Combustion, the rapid reaction with oxygen. And disproportionation, where the same element is both oxidized and reduced. The half reaction method provides a systematic way to balance any redox equation in acidic or basic solution. Redox reactions power our batteries, corrode our bridges, drive photosynthesis, fuel our cells, and extract metals from ore. Master these 5 classes, the half reaction method, and the oxidation number rules, and you can recognize, classify, and balance any redox reaction you meet in chemistry, biology, medicine, or industry. Thank you for learning with us.